Dear students, in the previous class we have discussed how to obtain a 95.44% confidence interval for the unknown parameter mu using the sample statistics x bar. Now in this class we generalize it. That is, we generalize the concept of confidence interval for any confidence level such as 95%, 99%, 90%. So we generalize the concept of confidence interval for any confidence level such as 95%, 99%, etc. Now, to begin with, we introduce some general notations used in the context of confidence intervals. Now, the first concept is we want to write confidence level in the form of 1 minus alpha. We want to write confidence level in the form of 1 minus alpha, where alpha is a number between 0 and 1. We write confidence level as 1 minus alpha. Alpha is a number between 0 and 1. For example, if confidence level is 95%, then 1 minus alpha is equal to 1 minus 0.05 is equal to 0.95. If confidence level is 95%, alpha is. If confidence level is 99%, 1 minus alpha is 1 minus 0.01 is equal to 0.99 or 99%. So alpha 0.05 means confidence level is 95%. Alpha 0.01 means confidence level is 99%, like that. Then the symbol Z alpha. So we write a confidence level as 1 minus alpha. Alpha is a number between 0 and 1. Then the symbol Z alpha denotes Z scores that has an area alpha to the right of the standard normal curve. So suppose that this is the standard normal curve, Z alpha is 1.96. Z alpha is 1.96. Then it means Z alpha means the area of Z, the standard normal curve, the value of Z corresponding to a certain level of confidence, the Z score that has an area alpha to the right. For example, if I write Z0.05, it means the area that is 5% to the right of this Z0.05. And Z alpha by 2 means Z score that has an area alpha by 2 to the right. Alpha by 2 to the right. So Z alpha means an area equal to say alpha. Alpha means 0.05 or 0.1, 0.005, etc. to the right. So Z alpha, say Z 0.05, Z alpha by 2. Say if alpha is 5%, Z 0.05 by 2 is equal to Z 0.025. So Z alpha represents Z score that has an area 0.05 or Z score that has an area alpha to the right. If it is alpha is 0.05, Z score that has an area say an area 0.05 to the right. That is the Z score, such as 1.96. So for example, if it is 1.96, the area to the right is 0.025, like that. Now, for any normally distributed variable, 100 into 1 minus alpha percent. For any normally distributed random variable, 100 into 1 minus alpha percent of all possible observations lie within Z alpha by 2. 100 into 1 minus alpha percent in percentage terms, say 95%, 99%, etc. of all possible observations lie within Z alpha by 2 standard deviations to either side of the mean. 100 into 1 minus alpha percent. So for example, if alpha is 5%, it is 100 into 1 minus alpha, that is 95%. If alpha is 0.01, 99% of the normally distributed random variables lie to either side of the mean. Either side of the mean. So given these notations, confidence level denoted as 1 minus alpha, Z alpha, 100 into 1 minus alpha percent. We now develop a procedure to obtain confidence interval for a population mean when population standard deviation is known. We explain the construction of confidence interval when population mean is assumed to be normal. Sorry, population mean standard deviation is known, and we assume that the variable under consideration is normally distributed. We assume that the variable under consideration is normally distributed. Now, if X is a normally distributed random variable, normal with mu and variance sigma square, so that standard deviation is sigma. X bar is also normal with mean mu and variance sigma square by n, and the standard deviation is sigma by root n. If X is normal, X bar is also normal. So this fact was used in the previous class to construct 95.44% of the confidence interval, and it was shown like this. Mu, this is mu plus 2 sigma by root n. This is mu minus 2 sigma by root n. In terms of Z, this is 2, this is 0, this is minus 2. In terms of Z, the distribution of Z. Generalizing this, we can generalize it as X bar mu plus Z alpha by 2 sigma by root n, mu minus Z alpha by 2 sigma by root n. And in terms of Z, this is 0, this is plus Z alpha by 2. and this is minus z alpha by 2. If alpha is 5%, as an example, this value is plus 1.96, this value is minus 1.96. So we will say that 100 into 1 minus alpha percent, 100 into 1 minus alpha percent equal to 100 into 1 minus 0.05, that is 95% of x bar lie between these two intervals. In terms of z, 95% of z lie between minus 1.96 and plus 1.96. So the confidence interval can be written as mu is equal to z alpha by 2 plus or minus sigma by root n. Mu is equal to z alpha by 2 sigma by root n. Depending on alpha, this value of the z vary from one alpha to another. If alpha is 5%, we will say that this is 95% confidence interval for mu. If alpha is 5%, this is 95% confidence interval for mu. And the interpretation is that if we construct intervals like this in a repeated number of times, mu will lie in such intervals 95 out of 100 times. So x bar mu is equal to x bar plus or minus sigma by 40. So the 900 into 1 minus alpha percent confidence interval for mu is x bar minus z alpha by 2 sigma by root n to x bar plus z alpha by 2 sigma by root n, or x bar plus or minus z alpha by 2 sigma by root n. And remember this, if the interpretation of the confidence interval is, if you construct confidence intervals like this in a repeated number of times, the parameter will lie in such intervals 95 out of 100 times. So this procedure is known as one mean Z interval procedure, or simply Z interval procedure. One mean Z interval procedure, or simply Z interval procedure. So let me explain the steps. And before explaining the steps, remember that this procedure is based on three assumptions. One, simple random sampling. Second, normal population or large sample, so that central limit theorem can be applied. 3, sigma is known. Then determine the confidence level 1 minus alpha. Determine the confidence level 1 minus alpha. And obtain the corresponding Z alpha by 2 from the table. Z alpha by 2. For example, if alpha is 0.05 or 5%, Z alpha by 2 is 1.96. Then the confidence interval for mu is, as I said, x bar minus sigma by Z alpha by 2 sigma by root n to x bar plus Z alpha by 2 sigma by root n. That is the 95% confidence interval for mu. Then, after obtaining the confidence interval, interpret the results. So, construction of confidence interval, if sigma is known, is very simple. You have an estimate, x bar, then it is assumed that this sigma is known. If sigma is known, construction of confidence interval is very easy. And in the example we have considered earlier, x bar was 41.4. We also assume that standard deviation is 12.1, and we establish a 95% confidence interval. And the 95% confidence interval is very simple: 41.4 minus 1.96, 12.1 by root 50, assuming that 50 samples are taken, to 41.4 plus 1.96, 12.1 by root 50. Assume that we take 50 samples. Population standard deviation is the earlier example. Sample mean is different because it is based on 50 samples. Then the 95% confidence interval is 38 to 44.8. 41.4 is the value, and we will say that the range is 38 to 44.8. And remember this, what is the interpretation of this confidence interval? The interpretation is that if we construct intervals like this, the true parameter will lie within these intervals 95 out of 100 times, or we are 95% confident that the parameter will be in the interval 38 to 44.8. Only 5 times the parameter will be outside this interval. Only 5 times the parameter will be outside this interval. So, this is how we construct confidence intervals using Z, assuming that population standard deviation sigma is known. When using this procedure, remember a few points. This procedure will work even if the population is not normally distributed and sample size is small or moderated, provided that the variable is not far from normality, and also that there are no outliers. If outliers are present, additional considerations are required. So this procedure is robust to minor variations or deviations from normality. So this is the one sample Z interval procedure. This procedure is applicable to all estimation testing procedures. So the procedure is very simple. Fix the confidence interval. That means fix the value of alpha. Obtain the value of Z from the table. Then construct the confidence interval. All the values are available. This will work if and only if this is known. And in most cases, as we will see later, this will not work because this quantity will not be known. That is it. And some additional points regarding this one sample Z interval procedure. One is, for small samples, say n less than 15, this procedure should be used only when the variable is normally distributed. For samples between 15 and 30, this procedure can be used unless data contain outliers or far from normality. For n greater than 30, this can be used without any restrictions. But if outliers are present and if the removal of the outliers cannot be justified, then you construct a confidence interval with and without outliers. If there is substantial difference in the confidence interval with and without outliers, then another procedure may be required or another sample may be required. And if outliers are present and if its removal is justified, you simply remove it and construct the confidence interval. If there is considerable difference between the width of the confidence interval with and without outliers.